Hello everyone, I'm Ahmad Attarha, a PhD student in Australian National University, Canberra, Australia. Today I'm presenting our paper named Network-Aware Co-optimisation of Residential DER in Energy and FCAS Markets, which is done by me, Paul Scott, and Sylvie Thiebaux. Also, I would like to mention that our paper was a part of a project which received funding from the Australian Renewable Energy Agency, or ARENA. In my talk today, first I'm going to talk about the problem that we are trying to solve. Then I walk you through the NEM, which is the electricity market in Australia. After that, I talk about our proposed distributed approach, which is then followed by some results and discussion. And finally, I finish my talk with conclusion and future work. These days, more and more distributed energy resources are being installed. As a result, the dispatchable generators, which were mainly in charge of providing frequency response, are leaving the electricity market. So while we are adding more volatility to our power system, we are reducing the resources that could actually mitigate this volatility. In Australia, for example, more than 2 million rooftop PV has been installed, and this number is increasing. As the market operator in Australia reports, in 2025, in some regions in Australia, rooftop PV will be sufficient to meet the demand. So in such a case, we either need to curtail a significant amount of PV to force in some of these dispatchable generators for the frequency response purposes, or we need to enable a more efficient way, which is enabling these residential distributed energy resources to bid in the electricity market. These DER are fast responding inverter-based technologies, so they can provide such a support. However, there is one problem here. The electricity markets are cleared at the transmission level, but these DER are mainly located and operated in the distribution network. In other words, we need to make sure that the distribution network constraints are taken care of before the bid reaching the electricity market. Let's quickly take a look at the literature. The literature can be categorized in two groups. The first one, which mainly neglect the distribution network constraint. So they just use a price-taking policy to schedule a DER and then their bid to the electricity market without the network. Of course, the price responsive behavior of DER can violate the grid constraint. For example, if there's a price spike, all the batteries want to discharge at the same time. This can easily go beyond the network capabilities. There are some works that use a central OPF to schedule the DER, like specifically fleets of DER. However, in our case, that we want to enable consumers to participate in the market, we have numerous consumers. Each of them have like thousands of variables and constraints. So we will end up with an optimization problem, which includes millions of variables and constraints, which is really difficult to solve within the time frame of electricity market. Also, even if you're able to solve such a problem, what we need to do is all the consumers and the grid need to send all their private information to one central tool to be able to solve a central optimization, which in terms of privacy is a bit difficult. Also, here in our paper, we want to actually enable consumers to participate in both energy and frequency market. Similar to the literature, we follow a price-taking policy. So because participation in one market might change the participation in another, we want to co-optimize our consumers to ensure that we can obtain the highest benefit. Also, as I said, it's important that our decisions are network aware, and also to capture the distributed nature of the problem and to ensure that our problem can be scalable, we use a distributed approach ADMM to solve our problem. Co-optimize and network aware actually are the two important terms that we also have it in our title as well. Okay, now that we know the big picture of what we want to do, let's take a quick look at the NEM, which is the electricity market in Australia. Frequency control ancillary service is, or FCAS, is a term that here in Australia we use for what mainly in Europe you know as reserve market. Like any reserve market, it's categorized into regulation and contingency. Here in NEM, contingency includes three markets itself, 6 seconds, 60 seconds, and 5 minutes. Each of these markets include a raise and a lower. So in total, we have 6 contingency FCAS market, 6 contingency FCAS market, and 2 regulation. In this paper, we only focus on contingency and energy. So in total, we solve 7, we co-optimize in 7 markets, which would be 3 raise and 3 lower contingency plus energy. Also, something else which is important about NEM is that in NEM, there is no day-ahead market, so the decisions are actually co-optimized in real time every 5 minutes. Okay, let's move to our approach. As I said, instead of solving a central approach, so here in a central approach, we need to have network and consumer data in one place, and then we solve everything together. What we want to do is to decompose the network, and each consumer, each of them have their own data, and they can solve their problem themselves. So we just need to communicate between these two sub-problems. So basically what goes from network to the consumer sub-problem is locational marginal prices, and what consumer sent to the network is connection point power. In more details, what we want to do is to minimize consumers' costs in energy and FCAS market, given some of the consumers' constraint and the network constraint. So this is a central presentation. X is the internal variable of the network, Y is the internal variable of consumers. So this problem cannot be decomposed because P is a common variable between network and consumer. To be able to decompose this, we actually duplicate this P to P and P prime. P would be the connection point power from the consumer subproblem from the consumer perspective, and P prime would be the connection point power from the network subproblem. If they now they can separately solve their problem. If they separately solve their problem now, of course, P and P prime would be 2 different values. However, we duplicate that and they should be equal. To enforce this equality, we write the Lagrangian of this equality constraint and add it as a penalty to the objective function of consumer and network subproblem. In other words, for consumer, we have the minimization that we had in the constraint plus this penalty. Here, they solve this problem and they obtain P, the connection point power from their own perspective. They send it to the grid. The grid uses this and obtains P prime, its own, the connection point power from grid perspective, and then we update the locational marginal prices or penalties that we have for P and P prime. So this iterative algorithm repeats until we converge. For convergence, we use actually dual and primal residual convergence, which more information about that is in the paper. The other thing is that I said that the electricity market in Australia clears every 5 minutes in real time. However, to make sure that our decisions are not short-sighted, we need to include the future time step as well. So for example, if we want to have a horizon of 24 hours, here we would have 288 time steps, which increases the size of the problem. An alternative for that we suggest was using 5 minutes for the first time step, and 30-minute discretization for the future time step. This can reduces the total time steps to 49, which reduces the size of the problem, and the problem can be solved faster. So in our experiments, we could our distributed algorithm converge 300 times faster at the expense of 2% benefit reduction for the consumers. Also, another benefit that our receding horizon either approaches can bring to the problem is that the uncertainty of consumers and the electricity prices, everything is changing. Every 5 minutes, this receding horizon let us feed our model with the latest uncertainty forecast, and then this way we can obtain a more accurate result also. I want to talk a little more about our approach in a nutshell though. So the consumer subproblem the constraint that they have can be categorized to markets linking constraint and some physical and operating constraint. So physical and operating constraint, I'm not going to talk about them here. They're in the paper. Basically, it's the battery, SOC, PV, and all the constraints that we have that we repeat for all the market that we want to participate. But for the market linking constraint, as I said, we have one for energy, 3 raise, and 3 lower. This M is the market counter, so it's 1 to 3. The raise and lower would be added or subtracted from the energy. So what grid sees is 1 energy, 3 raise, and 3 lower. However, we don't need to check the grid constraint for all these scenarios. We only need to check the grid for energy, most extreme raise, and most extreme lower cases. In other words, this P in iteration K that we obtain includes 3 vector variables: energy, extreme raise, and extreme low error. Similarly, the network also solves 3 OPF, one for energy, one for extreme raise, and one for extreme low error. For the network subproblem, we use this flow equation. I'm not going to go into the details of these flow equations. I'm going to skip it because of the time. So basically, again, we repeat these equation 3 times for each market, and our iterative algorithm keeps going until we converge to the optimum or near optimum solution. Okay, so for the test, for testing our approach, we use 2 test systems: 69 bus with 207 consumers, 141 bus with 1400 consumers. We use Groby and IPOP solvers in Jump Julia to solve consumer and network subproblems. We also explored 4 different cases in this paper. Energy, which we only participate in energy and not FCAS and not frequency. So as I said, our approach is both co-optimized and network aware. To show these 2 important parts of our approach, we develop a case which is sequential. Basically, we first participate in energy, and then the rest of capacity is allocated to the FCAS. Co-opt, which we co-optimize the decision, but we don't consider the network. And finally, the proposed approach, which is both co-optimized and network aware. Here I show the cost of different approaches. As you can see in energy, because we don't participate in FCAS, so we have some cost, but other approaches that participate in FCAS, they obtain benefit. So negative cost here is benefit. As you can see, both co-opt and proposed approach, because they co-optimize the decision, they have obtained much higher benefit. Also, another thing which is worth mentioning is that the proposed approach obtained slightly less benefit compared to co-opt. The reason is we have network. This is the cost of feasibility. The co-opt approach is not feasible. So this is the cost that we need to pay for the feasibility. Here we break down the cost to the energy and FCAS market. As you can see, the sequential obtains the minimum cost in energy market because it doesn't see the FCAS, so it just focuses on energy and minimizes this bit. However, both co-opt and proposed approaches, they see the FCAS, so they want to kind of co-optimize these approaches. They obtain slightly higher benefit, higher cost in energy, but they obtain much higher benefit in FCAS, which in total they have much more benefit. Okay, here we kind of want to show that how important it is to have this network aware part. The blue here we plot the voltage of bus 27. Bus 27 is an end node which kind of experiences the highest voltage swings. So here the first one is the normal operating condition, and here is when raise FCAS is also getting called. The blue line shows when there's no network, and a pink one shows a proposed approach which we have network. As you can see, when the network is neglected, the decisions actually the voltage of bus 27 is outside the safe limits, but when we include the network, our proposed approach manages to keep all the voltages within the safe operating limit. Here I show the problem size. As I said, consumers can solve their problem in parallel, and the network, because we decompose consumer and network, the time coupling constraint of consumers is not reflected in the network subproblem. So we can actually decompose the network in time and then solve each time step in parallel as well. So in parallel computation, we could solve the 69 bus network in about 3 seconds and 141 bus network in less than 37 seconds, which given the problem has like 5 million variable and constraint, this time is pretty good. Also, to show how important is to have this ADMM and distributed approach, we solve another case which we include a central approach. And in central approach, assuming that all the consumer can send their private information to a central tool, and we have no privacy issue here. The 69 bus network took more than 7 minutes, and 141 bus network took more than 3 hours to solve this problem. So this shows that the electricity market clears every 5 minutes. So both these times are obviously not good enough for us. Finally, in our paper, we show how important it is to co-optimize our resources, and also it's important to have network aware bits. We show that our distributed approach can scale well in parallel through parallel computation. And also we show that the variable time discretization can provide an acceptable trade-off between computational complexity and total cost. For the future work here in our paper, we only participated in contingency FCAS market, so in total 7 market. However, we can add regulation FCAS market as well. So in total 9 markets, for future work. And also here we follow the price taking policy. However, evaluating a case where aggregators or consumers are no longer price takers is something which is interesting to investigate. We worked a little bit on that also ourselves. Yep, that's it. Thank you so much for listening to my talk, and I'm here for your questions.
Thank you very much, Ahmad. There is one question written, but there was another. I will first give the floor to Jordan to ask question to Ahmad, since he asked me first. He's one of our panelists.
Yes, thank you. So yeah, my question is regarding how did you fix the price for the energy and the FCAS markets? Because the revenue from FCAS market seems much larger than the energy price.
Yeah, so there are 2 reasons for that. So we actually, all our data is coming from the Australian market. So here, AEMO website, which is cited in the paper. The reason that benefit in FCAS market is higher because in energy market, they are using electricity as well. So they are buying electricity and selling electricity. So it's a cost because they buy more than what they sell. But in FCAS market, they just sell. So that's pure benefit for them, right? So that's the reason that in FCAS, they obtain much higher benefit. One of the reasons. Also the price of FCAS, because it's kind of important, reserves are really important. In some hours, they have, like, the prices are like really high. So, and aggregators are fast responding, so they can participate. So they can enjoy the high price. So that's the reason. But yeah, the data is also cited in the paper if you're interested.
Okay. Okay, thank you.
There is a question from Raul Gupta. Thanks for a nice presentation. Usually ADMM algorithm convergence depends a lot on the penalty parameter. How do you choose the penalty parameter? Do you use some adaptive approach? And the question continues, have you faced any convergence issues with ADMM?
So the setting of ADMM, depending on how we use that, can be different, of course. In the paper, I think I mentioned also in the numerical result that the penalty for the raw penalty that we use is 1 for each market. We didn't use any adaptive approach for that. Yeah, it is possible to use adaptive cases, which can increase the convergence time, but we didn't use this in our paper. There is a guarantee that ADMM converges no matter what the penalty is. But yeah, of course, having an adaptive penalty can be another future work which we can explore.